For decades, power grids operated quietly in the background of modern life. They were complex but isolated. Power flowed, protection worked, and decisions were made locally. Then the grid went online. Connectivity transformed how electricity is monitored, controlled, and optimized. But it also transformed something else: the nature of risk. This video explores the moment power grids became connected systems, why engineers embrace connectivity, and how that single shift changed everything. For most of the 20th century, substations operated independently. Protection devices made local decisions. Control required physical presence, or at best basic signaling. There was no real-time system-wide visibility, no centralized optimization, no digital coordination. But as electricity demand increased and networks expanded, this operating model began to reach its limits. Utilities faced a new question: how do you see and control a system that spans thousands of kilometers in real time? The answer was connectivity. By the late 20th century, power systems had become national and even continental in scale, highly interconnected, extremely sensitive to cascading failures. Local protection alone was no longer enough. A fault in one region could propagate rapidly across the network. Operators needed wide area visibility and coordinated control. Connectivity enabled centralized supervision, faster decision making, and system-level optimization. It wasn't about convenience. It was about survival of the grid itself. Once communication networks were introduced, new capabilities became possible. Operators could remotely monitor substations. Generation could be dispatched centrally. Loads could be balanced dynamically. Faults could be located faster. Outages could be restored more efficiently. Operational costs were reduced. In short, communication transformed grid operation. At this point, connectivity was no longer optional. It was essential. This transformation was driven by SCADA systems, supervisory control, and data acquisition. SCADA allowed operators to monitor voltage, current, frequency, and breaker status in real time. Commands could be sent remotely. Generation and transmission could be coordinated from centralized control centers. For the first time, thousands of kilometers of infrastructure could be overseen from a single room. But SCADA systems were built on a critical assumption: only trusted operators would ever have access. Early SCADA systems assumed a closed world, private networks, known users, controlled environments. As a result, authentication was weak or absent. Encryption was rarely implemented. Cybersecurity was not a design priority. At the time, this made sense. The systems were isolated, or so everyone believed. To standardize communication between devices, utilities adopted protocols such as Modbus DNP3 IEC 60870-5. These protocols were engineered for reliability, simplicity, and low latency. Security was not the goal. Most lacked encryption, most lacked authentication, most lacked integrity verification. They worked flawlessly, as long as no one tried to misuse them. The introduction of IEC 61850 marked a fundamental shift. Substations became fully digital environments. Ethernet replaced hardwired connections. Object-oriented data models replaced fixed signal definitions. High-speed goose messages enabled real-time peer-to-peer communication. Protection, control, and monitoring began sharing the same network. Efficiency increased dramatically, but dependency on communication increased as well. At this moment, the power grid crossed a critical threshold. It was no longer just an electrical system. It became a cyber-physical system. Physical processes depended on digital decisions. Software errors could cause physical damage. Network failures could trigger blackouts. Cybersecurity was no longer an IT concern. It became a core power system reliability issue. For years, utilities believed their systems were protected by an air gap. In reality, that gap slowly disappeared. Corporate IT networks were connected to control networks. Remote access was introduced for maintenance. Vendors required online diagnostics and updates. No single decision removed the air gap. It vanished through hundreds of small practical choices. Connectivity brought undeniable benefits: faster, fault clearing, better situational awareness, lower operational costs, higher system utilization, but it also introduced new risks, remote attack surfaces, malware propagation, unauthorized control, cyber-physical cascading failures. The grid did not become exposed because engineers failed. It became exposed because progress has a price. There is no return to isolation. The future depends on smart grids, renewable integration, and digital control, built with security as a core engineering principle. Understanding this transformation is essential, because this is where real cyber attacks begin.